So welcome back. We're in the middle of sources of parallelism in locality and simulation. And so let me do a quick review of the few topics that we did last time, and we were in the middle of one, which was particle systems. So this was the motivation that we had, so that many real-world problems naturally have parallelism inside of them, because there's a whole bunch of objects that are moving independent of one another. And they also have locality because they naturally interact more with their nearest neighbors, whatever that means, than with their distant neighbors. And that gives us a very strong hint about how to assign work to specific processors to minimize the amount of communication that goes back and forth. And particles moving under gravity are a great example, and we will, in which the most progress has been made. So I will use that as a running example. And then when you actually take your real-world physical problem and write down a mathematical model, you discretize it, you say, I'm going to only solve it at certain discrete points, that usually introduces more parallelism. And we'll see that concretely as we do examples. So this was the outline of the 4 different kinds of problems that I was talking about. They're sorted in order from the most discrete to the most continuous. And most discrete means everything is discrete. You have a discrete set of variables, states, and they step forward in time, t equal 1, t equal 2, and that includes discrete event systems, simulating circuits at the level of gates, and Pac-Man, if you like. Then we started making the problems more continuous. We worked our way up to particle systems. And so a bunch of independent particles, so that's still discrete, but they're moving around under, say, Newton's laws, so their positions are continuous functions of time, that's continuous, and that's what we're in the middle of and we'll pick up on. And the next 2 things that we are going to work up towards are lump systems, again, a finite list of variables that you care about, voltages at particular places in your circuit, positions of particles, but now they're going to be more interesting continuous functions of time. And then finally, when everything is continuous. And so the goal also is to identify certain computational patterns that are going to come up over and over again in solving all of these, so that in later lectures I can sort of solve them once and for all, maybe, or at least tell you where good libraries are so that you can just sort of reuse the tools to solve those patterns that come up over and over again. So that's, let me scroll ahead to where we were in particle systems and try to pick up. So particles moving around, and let's see what I want to do here. Okay, so the interesting part about particle systems, and this is again slides we saw last time, is that once you know the force on a particular particle, everybody can in an embarrassingly parallel way say, where do I go in the next time step, right? You just update with your local information. The tricky part that's interesting to parallelize is how do you compute those forces? And there were 3 different kinds of forces that come up in different simulations. One is external, where everybody independently feels some external force, which could be the current in the ocean in the case of sharks and fish, or it could be some externally imposed electromagnetic field if you're an electron in some beam in some accelerator, or it could be the wind, if you're floating around, and you're a cloud. That's an externally imposed force. That's easy to parallelize. Everybody just should get an equal amount of work, no communication. The next harder thing is where you only depend on your nearest neighbors. And bouncing balls, really near neighbors is one example. But there are also things like van der Waals forces. It falls off so rapidly you basically ignore stuff that's far away. So there is communication there. You have to be close to your nearest physical neighbors in space. And so that gives us a constraint on how we parallelize it, assign work to processors, but it's not too hard. And then the interesting part, the really tricky part in which a lot of new algorithms are necessary is when everybody depends on everybody, 1 over r squared laws, gravity, electrostatic, stuff like that. And there's a whole bunch of new ideas there. And there'll be a whole lecture later in the semester, so today is kind of just an introduction. So again, let me just say a little bit about parallelism in nearby forces. This was the 2 pictures that we had, again, by way of review. So now I think I can go to slideshow. Yes, okay. So here the idea is that, let's suppose I have a square domain of particles. And I have 25 processors here arranged. As you can see, each box is a particle. Which particles do I assign to which processors? The most natural, intuitive thing to do is to assign each processor a square subgrid, and it owns all the processors inside that grid, and it's responsible for updating it. And so if all the particles are kind of uniformly distributed, that's an assumption, then everybody will have about an equal amount of work to do, and they can do local updates. So the question is, what about nearby forces? The whole hope is that if particles are nearby, like these two guys, they're going to be very likely assigned to the same processor, so no communication is going to be necessary in order to compute their nearby forces, assuming nearby is small compared to the size of these boxes. The only time that you might have to do communication is when somebody is really close to the boundary, so he might be very close to somebody who's just on the other side of the boundary. So the only particles that are going to need to be communicated are in these little blue neighborhoods, skinny little neighborhoods around the borders. And so how are we going to pick the shapes of these boxes? So I picked squares here, but what shape is the right shape? Well, I'd like there to be very little surface area, little perimeter in this case, so I don't have to communicate very much. And I'd like big blobs of space in the middle so that chances are that particles will be closer to the nearest neighbors. And so that's minimizing the surface to volume ratio of these shapes. And in the two-dimensional case, squares are kind of obvious. But this was a pattern we had before, surface to volume ratio. How do you minimize it? Now, there was an assumption here that I made, which is that particles are uniformly distributed so that everybody gets an equal amount of work. And it's pretty obvious that this processor has no work to do. So I need a different idea. I still want to minimize surface to volume ratio, but I also want a load balance. So the idea that people used in this business is something called quad trees, where I start by dividing the region into 4 squares of equal size, and then I look inside each one and ask how much work is there inside. There's 2 particles there. I'm not going to divide that up anymore. One processor is going to own that whole big square. This square up here in the northwest corner has lots of particles. I'll divide it again. He's empty. I'm not even going to assign a processor to that box. And I keep on going until I hit some minimum bound on how many particles I'm willing to assign to a processor. And here, since they're squares, I'm still kind of minimizing the surface to volume ratio, but I'm also doing the load balance. So those were the basic ideas for nearby forces. And now we get to far-field forces, where it's a much more challenging problem. So everybody depends on everybody else. You can't ignore any of, if you're doing your sum of gravitational sum and it's 1 over the distance squared, you can't ignore any terms and get the right answer. And so how you distribute the particles, doesn't help that problem. I mean, I could put all the particles on one processor, then no communication would be required, but I wouldn't have any parallelism either. So the simplest, most naive algorithm, and that actually attains a lower bound in a certain sense, is you give every processor here, there are 5 processors, each one gets n over p, n over 5 particles. They start by computing all the interparticle interactions just of the n over 5 particles they own, so that's n over 5 squared pieces of work, and then they just talk to their neighbors. They send a copy of their particles to their neighbor to the right, and each processor does the same thing. They just sort of pass around like you're sitting at a circular table. Then you take your neighbor's particles and you do all the interparticle interactions for the ones that you own. Then you take that copy and you send it to the next guy, and you do all those particle interactions, and you just pass things around p minus 1 times, and at the end of p minus 1 steps, you have seen every particle once, you've computed all the interactions, and you've had perfect parallelism. And if you're only allowed to have 1 copy of every particle, or maybe 2 copies of every particle, that algorithm is optimal. It hits a lower bound in how much you communicate. It turns out that there are clever ways to do arbitrarily less communication than that. If you're willing to sort of trade memory and communication, we'll talk about that in a later lecture. And even more interesting is this is an n squared algorithm, n particles, n squared work. You don't have to do n squared. If your forces satisfy certain nice properties like gravity and electrostatics do, there are algorithms that go down to order n log n or order n and give you as many decimal places as you like. So let me give you a hint. There's going to be a whole lecture later in the semester, and let me just give you a hint of what those algorithms look like. They both involve some approximation, but you can have as many digits of correctness as you want. So the first trick that people use is that they take each particle now, and let me now superimpose a mathematical mesh, not a particle mesh, on my square box of processors. What I'm going to do is take every particle and just move it artificially to this nearest point on this mesh, superimposed mathematical mesh. So it turns out that if all the particles are sitting on a nice square mesh like that, then there's a special algorithm that solves for all the forces, and it uses an algorithm called the fast Fourier transform, or the FFT. There's another version called multigrid, because when all the particles are sitting on a nice mesh, it turns out you're solving a very special system of linear equations called the Poisson equation, and it all goes super fast. So, but we're making an approximation because, of course, the particles have moved, so the forces aren't perfect, but it's good enough in many situations. So that's one example, and we'll have a lecture later on how you do FFTs in parallel and multigrid in parallel, because, I mean, FFTs are important for lots of things. So this is just one example of where you might use it. And the other one, which got many awards for the authors who thought of this idea, and I think I used this analogy before. Suppose you want to compute the gravitational force on the Earth. So you walk out at night, you look up at all those little white dots in the sky, and you think, I need a term in my summation for every one of those little stars. And then you realize that one of those little white dots is the Andromeda galaxy, which consists of another billion white dots inside. But no, you don't need to have a billion terms to approximate the Andromeda galaxy. The center of mass and total mass of the Andromeda galaxy gives you many decimal places. And in return, the Milky Way looks like a white dot to the Andromeda galaxy. Now, inside the Milky Way, our solar system looks like a white dot to people on the planet Vulcan. And whatever solar system Vulcan is in looks like a white dot to us. So this approximation works at every level. It works recursively. And if you do that recursively, the complexity goes down to either n log n or order n. And there have been many clever algorithms that have been published, and I'll have a summary of how, and people have worked really hard at parallelizing them. And there'll be a lecture later on the semester. One of them is called Barnes-Hutt, and the other one is called the fast multipole method. So that's sort of what people do to deal with distant forces if they obey nice laws like, well, Poisson's equation. Okay. So that's the end of particle methods. And so the model has discrete entities, positions of particles, and time is continuous. And so I have to sort of take time steps, so I have to make it discrete in order to solve it. And all the work comes down to computing three kinds of forces: external, which are embarrassingly parallel; near neighbors, which I can do by breaking up my region into squares of certain sizes, maybe with some care for load balancing; and then far field forces, where I have to be quite clever in order to avoid doing n squared work and just do n log n. So all of this you can think of as a special case of the next category. Are there any questions about particle systems before I go on to its generalization? So, which is lumped systems, okay, ODEs. So this is where, again, I just have a discrete set of variables. They could be particle positions, that's a special case, or they could be stresses and strains at particular girders in this building, or they could be voltages and currents in particular places in a circuit. So I have that discrete list of objects that are all functions of time, and I want to compute their values. But it's not true anymore that everybody has to depend on everybody, right? I usually have only a short list of other objects that I depend on. If you're a girder in this building, you're only connected to your girders that you're riveted to, right? So that's a very short list of all the interactions you have to worry about. And if you're in a circuit, it depends on where the wires are, and chances are there's just a few wires you're connected to. And all of that is going to lead to different, it's not going to be everybody depending on everybody anymore. It's going to be a very sparse set of dependencies, and that's going to be another interesting thing to parallelize. So, and the common mathematical object I'm going to use to describe all this is a graph. So every object that I want to simulate is a vertex, a point in a graph, and it has edges, which could be wires or rivets, connecting it to all the other objects in which it depends, and that's going to be the mathematical abstraction that I use to solve all these problems. It's called lumped because I don't care about the voltage along every point in a wire, just at the endpoints. And and we all can write down the equations. Depending on whether you're an Eekes person, you'd write down Ohm's laws and Kirchhoff's laws, and if you're in civil or mechanical engineering, you'd write down F equals Newton's laws and Hooke's law for springs and stuff like that, and you can write down the equations. So in addition to plain old ordinary differential equations, this is actually more general, because when you write things down naturally, not every equation has to have a derivative in it. It may just be a constraint, right, that this has to match that. And so, for example, Kirchhoff's laws say all the currents in have to equal all the currents out. So you get some linear equations without derivatives, and you get some derivatives too. It's all part of this model. And so here is, the well-known model, just to write it down really explicitly for electrical engineers. So I have node voltages, the voltage at each vertex in a circuit. I have the currents, which how much is flowing along a particular wire or branch B. And I have the branch voltages, what's the voltage difference from one end of the circuit to another. And then I just write down a whole bunch of equations, all the physical constraints that describe it. So the first set of equations is Kirchhoff's current law that simply says all the current into a node has to equal all the current out of a node, just conservation. And so how do I write that down? Well, what I do is I have a big sparse matrix A with a lot of ones and negative ones in it that simply says who is connected to whom in my circuit. It's just a way of writing that down. And when I multiply, and when I look at this first equation, it just is A times the vector of currents equals 0. All the ones and negative ones in that big sparse matrix simply sum all the ingoing and outgoing currents at every location. Kirchhoff's voltage law is pretty much the same. The voltage, along one wire is, the difference of the voltages at the endpoint. So this is just another simple linear equation, but with a transpose of that same big sparse matrix. Then I get Ohm's law, so I get a diagonal matrix with resistances in it. Still no derivatives. Finally, I get derivatives because I have capacitance times derivative, and I get inductances. So there's derivatives and not. And so this is a huge sparse matrix. The number of non-zeros in this matrix is really just the number of wires, right? Which is not n squared. It's whatever small number it is, but that's what I want to solve. And if you're in a different department, you would write down the same thing in structural analysis, and there's a big project here, as you probably know, in civil engineering, to build a big parallel simulator for large structural engineering problems, and they looked, why did the freeway fall down back in the Loma Prieta earthquake? So they've done lots of interesting simulations of that sort. But if you're interested in making money, then all of this comes up in gaming as well. So let me just do a little video here. All right, let's. So this is work that was published by James O'Brien here in Computer Science. Hello. We won't watch the whole video, but we'll watch a little bit of it. So if you buy a computer game these days and things move around, it's doing real-time parallel finite element simulation of everything that's crashing and breaking. So, and it builds a finite element model of every last piece of stuff in there. It has different models for stone and glass and metal. And depending on what Darth Vader decides to hit or you decide to hit, it does the real-time simulation. And it has, different, this is on an Xbox, so it's, like 8-way parallel, but it's, bigger machines give you more things to do. And of course, you produce the sounds the same way. When something gets hit, it vibrates, you have a sound model, its eigenvalues and eigenvectors, that tells you what sound gets produced. So let me just move ahead a little bit here, pass the gameplay to different materials. Okay, so there's wood in it too. So there's lots of different kinds of materials you can do. Okay. So I'll just illustrate some of the different material simulations they do. Okay. So obviously different material parameters here. All right. Oops, went the wrong way. Back we go. Okay, let me just skip ahead a little bit here to another material. Plants. So those come up in these games too. They're much more elastic and plastic than glass, and they don't break, but they move around a lot. So you got to get that right. And they're very composite materials. So let's see. So you can see that it breaks in different ways. Okay. So not even Darth Vader can knock that tree down. It's too big, but he gets the bark off. Okay. Okay, so there's one more part I want to show of this. Let me just wait till this thing breaks. Okay. So smashing wood. Okay, here we go. So now we're actually going to see what the underlying computation is. There's the grid. There's the finite element grid that's used to do the simulation. And you can see it's quite coarse because there's a finer grained model for what the materials look like, but it does actually do the physics at the level of this granularity. Now, you can actually change the physics. We'll see that in a second. There's a pull-down menu to change the Young's modulus and Poisson ratio, and if you're in mechanical engineering, you know what that means, so it turns into jelly. But the game still works, and it just bounces around a lot. So you get the idea. So all of this is now how games are built. Let's go on to the, see if I can get back to the lecture. But anyway, so there's lots of uses for this kind of material. Okay, so let's talk about how we actually solve these things now. And so in the example that I showed you, where I wrote down the equations of the circuit explicitly, but in all the others too, the matrix is very sparse. And so it's not like n-body where everybody has to talk to everybody else. With gravity, it's a very sparse problem. There are only a few interactions. That's going to give us a different challenge in terms of how we paralyze it and assign work to processors to minimize communication. So there are two different approaches that people use to solve these ones, and they're going to lead to two different algorithms or two different computational kernels. One of them is called explicit methods, and the other one is called implicit methods. So let me just give a little mathematical review of what those are, and then talk about the kernels that they involve. So explicit methods, the ODE is written up here. I'm going to take the simplest example where x prime is a times x. A is a big square sparse matrix, and x is a vector. And so and here's a solution, or this red curve that I'd like to approximate. And of course, I'm only going to approximate it at a bunch of discrete points, so t sub I plus 1, where I take these discrete time steps of delta t. So how do I figure out what to do? Well, what does the ODE tell me? It tells me the slope at every point in that curve. So if I happen to be here, this equation, a times x, tells me the slope. So all I'm going to do is move along that straight line until I get to the next point. That is a classical method called forward Euler. And so what I'm going to do is, here's my approximate derivative. This is x dot of at x sub I. And that's going to equal the slope at this point, x sub I. And so if I solve for the value of x at the next time step, I know x sub I want x sub I plus 1. There it is, a simple one-line formula, and all the work is this matrix vector multiply. My big sparse matrix has to get multiplied by my vector x, and that's where all the work is to parallelize and to minimize communication. And we will have a lecture on the details of that later in the semester, but that's sort of the bottleneck in direct solutions of ODEs and many other things too. Now, the trouble with this method is that if your problem is changing very, very rapidly, because things are moving very quickly, then you may have to take incredibly tiny time steps to get the right answer. And so sometimes people say, I'm not willing to do that. I want to take larger time steps. And in that case, you need a different algorithm. And that's what are called implicit methods. So it's almost the same picture. Here is the curve that I'd like to follow, the same true solution. I'm still going to use the fact that the ODE tells me the slope at every particular point I'm at. And the only difference is, instead of using the slope at the beginning of the interval, which I did last time, I'm going to use the slope at the end of the interval. I'm going to use that straight line. So if I plug that in, everything is the same, except wherever I had x sub I change it to x sub I plus 1. And so now I write down, here's x dot of t, so there's the approximation. Now here's the slope at time I plus 1. If I solve for x sub I plus 1, I get a system of linear equations I have to solve. And A is part of the coefficient matrix. So I have now a large sparse system of equations to solve to get from time step I to time step I plus 1. And it turns out that lets you take much larger time steps. On the other hand, solving a large sparse system of equations is a lot harder than doing a matrix vector multiply, and whether the trade-off is worth it or not depends very much on the special properties of your problem, what your sparse matrix looks like, and that's a later lecture. But those are the two canonical approaches, and which will justify, among many other examples, why we're going to talk about sparse matrix vector multiply and solving later. So there's one other example that comes up that uses these kernels, and that is asking about modes of vibration. So in particular, the sound in that game, what are the frequencies? Those are the eigenvalues of the matrix that vibrates. When you build a building like this, and you want to know will it fall down in an earthquake, you write down the matrix. It describes the who's connected to whom and the stiffness and the mass of this building. And what do you ask? You ask what are the eigenvalues of this building, of that matrix? And if because those are the resonant frequencies that this building likes to vibrate at. And if those happen to match earthquake frequencies, well, you better change your building design because it'll go into resonance when you have an earthquake and fall down. So how do you go about solving that particular problem? So again, when you write down that differential equation, it turns out to be x double dot, second derivative of x equals ax. You say, I want to know what modes of vibration does it like. That means I'm going to assume the answer is a sine curve. So it's going to be a fixed shape of the building, which is vibrating at some frequency omega naught. And this is sort of reviewing math 53 or 54. You plug that in, and the sine function cancels out, and you discover that x naught, the shape of vibration, is an eigenvector of this big sparse matrix A, and the frequency squared, the negative frequency squared, is an eigenvalue. So it all turns into an eigenvalue, an eigenvector problem. And all the algorithms for that, again, depend on either sparse matrix vector multiply, the same thing that we did before, or they depend on solving big sparse systems of linear equations. So again, this is just to motivate the fact that we're going to come back to those problems later. I won't go into details about eigensolvers. There's plenty of good packages which in turn need to call good parallel implementations of sparse matrix vector multiply. And if you're interested, we can talk about that later. So let me say that for eigenproblems or for the implicit solvers, we have to solve this big sparse system of linear equations. There's two kinds of solvers that people use. The first one is called direct. It's sort of generalizations of Gaussian elimination, except it takes advantage of the fact there are lots of zeros. And the algorithms don't store the zeros, don't work on them. So you need very interesting data structures and algorithms to avoid doing all that amount of work. And it's called, the name for this is called LU decomposition because you're going to factor your big sparse matrix A into the product of a lower triangular matrix and an upper triangular matrix. It's just the way people talk about Gaussian elimination. And we'll have some future lectures about that. And for iterative solvers, there's a whole bunch of different algorithms. And again, we're going to have another lecture on that later that depend on the structure of your matrix and that iterate in different ways. What they all have on the inside of them is sparse matrix vector multiply for some matrix that you maybe derive from your input one. So let me just say a little bit more about how sparse matrix vector multiply is implemented, because that's kind of a kernel operation that we use all the time. So what I want to do is use a data structure that requires me not to either store or do any arithmetic with any of the zeros in the matrix, right? That's just wasted stuff. So here I have a picture of my sparse matrix where I've color-coded all the non-zeros. The white entries are 0, don't want to do any work. And so I want to multiply A times X, X is up here, and come up with Y. And so the data structure is simply going to take every row of my sparse matrix and pack all the entries together and throw away all the zeros. So these 4 non-zeros in the first row just get packed together. The next 3 non-zeros in row 2 get packed together. But of course, I have lots of information. I have to record where did they come from. So I need another array which remembers the index. Which column do they come from? So here, this comes from columns 1, 2, 5, and 8. So these numbers here would be 1, 2, 5, and 8. And then I also have to remember when does row 1 end and row 2 begin. So I have yet another little data structure that just points to the beginning of each row. So that's my data structure. And then what does the simplest implementation look like? Let me just write down the sequential code. So I want to do basically a dot product of every one of these rows with X. So there's what I'm going to do. So there's the 2 nested loops that, matrix vector multiply is naturally 2 nested loops. So for each row, I'm going to compute the dot product of the ith row of A with the vector X. And how many locations do I have to iterate over? Well, I look at this guy and I says, well, I got 4 in the first row and 3 in the second. So that's going to be, the pointer array is going to tell me how far to iterate. And here's the dot product. And the interesting thing is that I have this index here, indirection. I have to go into memory somewhere and look up where the vector, the entry of the vector X is. Because here I need X sub 1, X sub 2, X sub 5, and X sub 8. And they may or may not be in your cache. They may not, or may not be on the same processor that you are. So that's why the parallelism is an interesting question. So let us ask ourselves how to parallelize this and what problem comes up if we want to do it in an optimal way. So again, it's y equals a times x, and let's suppose I have 4 processors. a perfectly natural thing to do is to give each processor 1/4 of the rows of the matrix and say, you, processor 1, please compute the product of that submatrix of A with that vector X, and please put your answer up there. Right? That seems like a natural thing to do. So the questions that we have, that's one answer. The general questions is, which processors are going to be responsible for storing every particular entry? The first quarter goes to processor 1 is only one answer. Who owns X and who owns Y? And which processor is going to be responsible for actually doing the dot product? So the general answer is, what we're going to do is take all the rows of this matrix and partition them. Here I've partitioned them into 4 equal sets, but that's not necessarily the right answer, and I'll show you why. But I'm going to partition them into P sets of rows. So I'm going to take all the rows and break them up into P pieces so that processor 1 is responsible for those rows and processor 2 is responsible for those. I'll say that processor K is going to be responsible for the same subset of the entries of X, of Y, and the same entries of X. So everybody sort of gets one subset of the indices, and that's what rows of A they own, that's what entries of X they own, and that's what entries of Y they own. And so now, when it finally comes time to do the work, I have to compute this dot product. And so the first processor is going to own all the data from A that it needs. No communication is necessary. It's going to own all the destinations, also the Y sub I that it needs. No communication. The problem is that it may not own all the X's that it needs, right? So that's where there's an optimization problem to solve. So what's the best case? The best case is no communication. What would my sparse matrix look like if there were no communication in this? If you always owned your X's, if you just sort of drew a picture and MATLAB would be a spy plot of the matrix, what would it look like? It would look like this. It would look block diagonal, okay? So there would be no zeros, no non-zeros off here, and processor 0 would own everything it needs, all the entries of A, all the entries of X, and all the entries of Y. Well, that's too good to be true for most matrices. You can't find an ordering that makes things look like that. But we'd like to get as close to this as possible. There's some metric that says I would like to partition the rows and columns of my matrix to make it, in some sense, look as close to block diagonal as possible. So let's just sort of write down, and this is going to turn out to be a problem we've seen already. So what are the goals of reordering? Well, I want to balance the load. I want every processor to have about an equal number of arithmetic operations to do, so it takes an equal amount of time. And so, and since I only do two multiply and an add per matrix entry, so that's sort of evenly dividing up all the matrix entries. I also want to balance the storage so that one processor doesn't have to use a lot more memory than others. That's obviously the same solution. Every processor is going to have an equal number of non-zeros, so these two problems are going to get solved the same way. So then, the hard part is I want to minimize communication. I want to minimize how many X values a processor has to go get from a neighbor. And so which in this picture is, I want to minimize the number of non-zeros out here. I want to make all the non-zeros as close to the diagonal as possible. And then there's a lot of local optimizations, that I want to, make my cache as well used as possible, use my registers. You'll have practice in homework 1 on that. So this is the goal, and the question is, how do I now formally solve this problem of giving everybody an equal number of non-zeros in the matrix, but minimize the amount of communication that I have to do to go off and grab stuff? And this is the problem that I think we already looked at. It's called graph partitioning. It came up in the discrete problem. So here's my sparse matrix, and let's suppose that I have 3 processors I want to assign it to, and so the non-zeros are just located here. And I'm using the fact that there's 2 mathematically equivalent ways to write down this matrix as a matrix and as a graph. So here I have 1 vertex for every non-zero in this graph. So I have 6, it's a 6 by 6 matrix, so I have 6 vertices numbered from 1 to 6. And I have edges whenever there's a non-zero. So here there's the entry 1, 4 is non-zero, so I have an edge connecting 1 to 4. And there's an edge from 2 to 3, so I have an edge connecting 2 to 3. So it's just a different equivalent mathematical idea. So what I'd like to do is ask, is this a good partitioning? If I assign, processor 1 gets rows 1 and 2, processor 2 gets rows 3 and 4, then have I done a good job of minimizing the amount of stuff that's outside the block diagonals? So here's the same thing in the graph picture. I'm going to put 1 and 2 in one partition. Let me just draw a circle around them. I'm going to put 3 and 4 in a second partition, 5 and 6 in the last partition. And I want to count how many edges are there that connect different partitions. Because each edge corresponds to a non-zero, corresponds to communication. So what I want to do is be able to draw these partitions, this is one possibility out of many, to minimize the number of edges across from one to another. So that is the graph partitioning problem that we alluded to for the discrete event simulation. It comes up here just as well. Okay, so let me just summarize. Here are the common problems that we saw for everything so far. There's been load balancing problems. So this is for both particle methods. So this is a summary for discrete event systems, for particle methods, and for ODEs. There was load balancing, giving everybody an equal amount of work to do. And there are different answers depending on whether things move and the load balance changes over time. And that's the dynamic case. In the static case, like the problem I just talked about, where I have a fixed matrix, then I can use graph partitioning. And that will, if I solve that well, tell me how to divide up the work to sort of optimize things over the entire course of the run. Linear algebra came up over and over again, both sparse and dense matrices. And then we also saw there were these very clever algorithms, which I'll come back to in later lectures as well, fast particle methods. So where I can compute, the gravitational forces on n particles, not in n squared time, but in order n. So this picture we've seen before, I just want to bring it back to sort of say this is an organizing principle for a lot of these lectures. We've been mostly talking about high-performance computing, and we've been identifying certain kernels marked by these red boxes that come up over and over again. We've seen work on dense matrices, sparse matrices, FFTs, they've all come up. And so these are sort of the examples to sort of motivate the fact that we are going to spend our time talking about how to optimize these later. But we did this, when we began the Parlab, we recognized that these 7 things marked in red were perfectly adequate for most of scientific computing. But we also asked ourselves, well, what about the rest of computing, commercial computing, everything else? And we said, well, is there anything more than the 7? And the answer was there were 6 more. There were 6 more kernels, which include things like finite state machines, doing combinational logic, doing graph traversal. I haven't talked about graphs very much. Those come up in embedded computing, in the spec benchmarks, in databases, in games, in machine learning. And so eventually, during the course of this semester, we will have to talk about all parallel algorithms for all of these different building blocks that you can use. So it'll take a big chunk of the semester as we work our way through parallel algorithms for all these. So that's the end of 3 out of the 4 parts of sources of parallelism. So we talked about discrete event, particle methods, and ODEs. And the next one is PDEs. But before I go on, any questions? Okay. So I think you made all the course announcements that you wanted to.
Yeah, you can tell people that they should
with a micro.
Sorry. You can check again to see if your partner is online and if you've not.
For homework 1, yeah.
For homework 1, I'm sorry. And make sure you can get in touch with them via email. I purposely didn't put the email addresses on the public-facing website. So email the GSIs, myself, if you can't get in touch with your partner. Thanks.
Okay. Very good. So here's a recap of what we just did. So we have already talked about discrete event, particle systems, and ODEs, and now it's time to go on to PDEs. And the common problems that we're going to see again is how do I divide the load up well? And there was static and dynamic. How do I maximize locality, minimize communication? And recognize the fact that there's a tension between these two. If at every step I have to rebalance the load, that's going to be a lot of communication, right? So we'll have to compromise somehow between doing these. Okay, so now we're going to talk about parallelizing these. Yes, question? And let me pass you the microphone.
So the graph partitioning problem is like really hard.
Graph partitioning is NP hard.
Right.
We will approximate it.
Okay. So you're going to talk about that later?
Oh, absolutely. So there will be a whole lecture later in the semester on that graph partitioning problem. If you can't wait, you can look at the posted lectures from last year. But yeah. So many problems, it turns out, in combinatorics are NP hard, and for those of you who are not computer scientists, that means if you want the exact solution, you want to solve it perfectly so that you have the best possible load balance, the only algorithms people know are exponential in cost, 2 to the n. So it just totally overwhelms everything else that you want to do in the problem. So we have to settle for approximations. And if we're close to communicating as little as possible, that's certainly good enough for almost all practical purposes. OK, so let me just sort of describe the problems I'm talking about. So now everything is continuous. The solution is a function of both space and time. And there are 3 different classes of problems that all parallelize in slightly different ways. They come up over and over again. So they're called elliptic, hyperbolic, and parabolic equations. And elliptic equations, think gravity or electrostatics. There's a constant answer, which is the potential, gravitational potential, or electrostatic potential. It depends on space, not time. And so what I want to do is solve an equation, and I want to get an answer which gives me the potential as a function of position. And of course, I'm going to have a discrete grid of positions that I want to evaluate it at. So no time dependence. Next example, there is time dependence. Things are moving. And the canonical example is waves moving around. They could be sound waves or earthquakes or anything like that. And in that case, again, I have the answer, which may be the pressure from the wave, is a function of position, but it's also a function of time. But something that's really useful about these problems is that the waves move at a finite speed, right? There's a velocity of sound, a velocity of stuff, vibrations. So information can't move very far, right? You're limited by the physics as to how much you have to communicate, and we will take advantage of that. And then the third class, which is maybe the hardest, is called parabolic. You have time dependence now and space dependence, and heat and diffusion are the canonical examples. But now, at every time step, information in principle moves infinitely fast. At every grid point, when you want to update the temperature, you have to know everything at the previous time step. That is so it combines the idea of hyperbolic, things are moving, but it also has all the challenges of elliptic, because everything depends on everything, and we're going to have to be clever to not communicate that much. So I've distinguished here between global versus local dependence. Global, that's like elliptic and parabolic. Everybody depends on everybody. Versus hyperbolic, where it's only nearest neighbors because there's a finite speed of wave propagation. And of course, in real life, when you write down your equations, and you're doing fluids or elasticity, you combine these features. But these are sort of the main high-level features. So to write down an example, let me start with what Fourier did in his lab and just write down the one-dimensional heat equation and use that as a running example of what we have to do. So here I have a one-dimensional bar. It's really hot, glowing red at one end, and it's ice cold, blue at the other end. And I want to write down an equation for the temperature, U, at every point, x as a function of time, t. And so here is what you observe, what Fourier observed in his lab. How fast is the temperature changing right there in the middle? Well, the answer depends on how much the temperature changes between x and x plus h, how much it changes to the right, how much it changes to the left. Subtract those, and it's how much it changes right there. And if I let h go to 0, you get the heat equation. The derivative of the temperature with respect to time is some constant, the conductance times the second derivative with respect to x. And so the intuition is, if this is a temperature +1, 0, and -1, it's not going to want to change the temperature here in the middle at all, right? It's just going to stay nice and stable at 0, because it's halfway in between its neighbors. But if the temperature here were 1 on that side, 1 on that side, and 0 in the middle, your neighbors are hotter, you're going to want to warm up. That's all captured in this equation. So this is what we want to discretize and write down simple equations, and eventually in higher dimensions. But let's just do it in one dimension first. So there's the equation. And what I want to do is discretize time and space and just write down what happens not at every continuous x, but just x at a bunch of discrete grid points, and the same for time. Time t = 1, 2, 3. And I'm going to use an approximation, and it's going to be the same one I did in the last lecture, forward Euler, to approximate the derivative. So here's the derivative. So here's the derivative with respect to time. It's the temperature at t plus delta minus the current temperature divided by delta. That's going to be my approximation there, a straight line. And here's going to be my approximation for the second derivative. I take the first derivative to my right, the first derivative to my left, subtract and divide by h. It's sort of the simplest way you could write down an approximation of a second derivative using straight lines. So, and if I just combine all the terms, I see it depends on the temperature right where I am right now, a little bit to my right and a little bit to my left. So just my 3 nearest neighbors, my 2 nearest neighbors and myself, that's all I need to know. in order to do this update. So now I'm just going to take that and solve for the, so I'm going to assume I know the temperature everywhere at time t, and now I want to know the temperature a little bit later at time t plus delta. So I'll just solve all that. And I get this explicit equation. The temperature at time t plus delta at location x is this nice simple linear combination of all the temperatures at time t and at x, just a little bit to my right and just a little bit to my left. Okay, let me simplify this so the notation so I don't have to carry it around. Let me just take all that constant and collapse it into one constant, call it z. And so here is what I get. I get a z times my neighbor to the left, z times my neighbor to the right, and 1 minus 2z times my own value. And this is all just notation, so I can finally write down algorithms. And so what I'm going to do is only evaluate this at a discrete set of points. So I'm going to do it at x equals 0, x equals h, 2h, 3h, 4h, so just a nice even set of grid points. And I'll do the same thing for time. The time equals 0, delta, 2 delta, 3 delta. And I'm going to use integer subscripts now. So I'm just going to switch to integer subscripts. The first subscript is space, and the second one is time. And so there, finally, is the equation that I need to do the updates on. So let me now just draw a picture. So write down what I had before. Here's the algorithm. I'm going to go from time equals, so to go from one time step to the next. So to go from time step I to I plus 1, I'm going to loop over all the space indices and just evaluate that expression that I had in the previous slide. And here's the grid. Here's all of space, from the left end of the bar to the right end of the bar at time 0, time 1, time 2, time 3. And to update that value, I need the 3 values of the temperature at the previous time step. And so this, now that I've done all that algebra, I hope we recognize, I'll write it down explicitly in the next slide, how do I get from time step I to time step I plus 1? It's a matrix vector multiply. All I'm doing is taking a linear combination of this vector lying on its side of temperatures to get this next vector of temperatures lying on its side. So it's, again, a sparse matrix vector multiply. And I'm going to call the matrix that's implicit in this thing T. And now let me write down T, just to be very concrete. So there's the inner loop of the algorithm again. And I'm going to just put it all together and say that to get from time step I, all the positions, to time step I plus 1, all the positions, I'll do a matrix vector multiply times this nice, simple, tridiagonal matrix T. It's tridiagonal because I only depend on my right neighbor, my left neighbor, and my own value. And I'm going to factor out the z and write this as identity minus z times L. And L is this famous matrix with 2's down to the diagonal, minus 1's off the diagonal. It's called the Laplacian in one dimension. So the whole algorithm consists of taking all the temperatures at one time step, multiplying by this very simple sparse matrix to get the value at the next time step. And if I were in 2 dimensions, I would have, of course, not this simple Laplacian. I would have a more complicated one. We'll see it later. But again, I'm only going to depend on my nearest neighbors on a grid. So I've just written it all down explicitly in 1 dimension. So, and no surprise, it's sparse matrix vector multiply all over again. But if it's a particularly simple sparse matrix, right? It's tridiagonal. What could be simpler? It turns out it's not so simple. We'll have lots of clever ideas to make it go fast. So how am I going to deal with this in general? Well, we've talked about graph partitioning. Here, it's really easy to see. If I have 4 processors and 12 grid points, everybody gets an equal amount of stuff. And I only have to talk to my neighbors, so there's the least communication you can imagine. There's one edge connecting this partition to the neighbor. So that's an explicit approach. People often use it for, as I just described it, when you solve wave equations. Information doesn't move very fast. But let's see what goes wrong if I actually use this algorithm for the heat equation. So the trouble is that it's not numerically stable. If I use this algorithm as I just described it, this number z, which was the conductance times the spatial time step divided by the space step squared, if that is bigger than a half, then there's a theorem that says you get garbage answers. It blows up. That tells you that you have to take very, very tiny time steps. If you cut your space resolution in half, you have to take 1/4 as big a time step. And so this is okay for if you have a wave equation, but it's not very good for the heat equation. So here's just an example. I'm going to take my my bar, which is ice cold blue at the ends, and it has a high temperature in the middle. It's glowing red, so the vertical axis is temperature. And I'm just going to keep the two ends in ice, so it should all cool off. And so here's the solution. If I take a time step which is just barely small enough, and indeed it cools off as you would like, then I make it just slightly bigger above that magic threshold, and it starts cooling off, and then it starts blowing up exponentially. So this is just the nature of these algorithms, and so we need an alternative, right? So we don't have to take really, really tiny time steps. And so let me come back. So everything I've talked about is called the explicit method. Every time step is a sparse matrix vector multiply, and it has this problem. So let's go look at an alternative. And just as for ODEs, I had explicit and implicit. I'm going to have explicit and implicit here. And so let's see what the implicit solution looks like for the heat equation. So there it is again. I'm going to discretize time and space just as I did before, take mesh points in the x direction, take mesh points in the t direction. And now I'm going to use, instead of forward Euler, instead of approximating the derivative at the current time step, I'll approximate it at the next time step. And so here's the algebra. It's just the same algebra as before. The only difference is I used to have a t there. Now I have t plus delta. So I'm going to approximate the second derivative at the next time step, not the current one. So I simplify it, and I use the same change of variables. I let z be this constant. I discretize, I change time to I, and I change space to j. And so now, instead of doing a matrix vector multiply to get from time I to time I plus 1, I have to solve a system of linear equations. It's the same problem that I had in the ODE case. And what's the matrix, the coefficient matrix in my system of linear equations? It's the identity plus z times the Laplacian. So it's a tridiagonal matrix. There's minus z's on the off diagonal and 1 minus 2 z's on the diagonal. And so, yeah, so that's what the matrix is. So it's the same matrix we saw before, except now I have to not do a matrix vector multiply with it, I have to solve with it. And that will let me take big enough time steps that I don't spend too much time, right? So this is going to be harder to make run fast, but since I can take bigger time steps, it'll be faster overall to solve my problem. So here I'm going to write it down again. So I have to solve a system of linear equations to get from time I to time I plus 1. And here's a system of linear equations. And for those of you who've studied this before, you've probably heard about a variation on this. It's called the trapezoidal rule that lets me take even better time steps. And it turns out you have to do both of the things I did before. You have to do a matrix vector multiply with that sparse matrix. That gives you the right-hand side. And then you solve a system of linear equations, and all I have to do is change the constant from z to z over 2. So what people actually do in practice, they do both. There's a sparse matrix vector multiply at every step, and then a solve. So they're both what people do in practice, called the trapezoidal rule. So that's what we got to parallelize. And so this comes up all the time. So we will have a number, 1 or 2 lectures later on fast algorithms for solving Poisson equation. So let me try to relate Poisson, and again, this may be a review for many of you. Why do I care about Poisson? What does it have to do with gravity and electrostatics? So this is, Physics 7 review here for a moment. So if I want to compute the force in the particle, which is located at x, y, z, due to a particle at the origin, and it's either gravity or electrostatics, here's the classical formula we all learned. It's the vector pointing from the particle back to the origin divided by r cubed. This is an inverse square law, right? So the size of this vector is 1 over r squared. So the way you can solve this is that the force, this is the force you want, it's the gradient of the potential. So if I can actually compute the potential everywhere quickly, I can just differentiate it, get the forces. And so what I would like to do is solve very quickly for the potential, and then I can get the forces. And it turns out the potential satisfies Poisson's equation, which is why it comes up over and over again. And I will let you plug in v equals minus 1 over r into Poisson and confirm that it does indeed satisfy it. So just to remind you of the basic physics, which is why it comes up over and over again. OK, so that's about the 1D problem. Here's what the matrix looks like in the 2D case. And so let's just see why it looks like this. I'm going to have 4 times my own value. I have my neighbors to the left and the right. And then I have my neighbors above and below. So where does this ordering come from? If I have a 2D mesh and I have 4 neighbors, I have to choose some ordering to order all these non-zeros in. So if I order it, say, from the first row, followed by the second row, followed by the third row, my neighbors to my left and right are right next to me in order. But my neighbors above me and below me are a little bit farther away. They're a distance Well, if that's n, they're a distance n away. So I get this band matrix, but this band here is a certain distance away. It depends on the size of the grid. So that's the matrix that I have to solve. It's not tridiagonal anymore. It has 5 diagonals, but it's kind of spread out. And so it requires much more clever algorithms to deal with this particular problem. So what I'm going to do now is put up a table of all the possible algorithms that could be used to solve this problem, sorted in order from fastest to slowest. Sorted in 2 orders, from fastest to slowest, just to sort of give you a survey. And from most general, they solve lots of problems besides Poisson, to it only solves Poisson, but as fast as you could possibly go. So here's a list of all the algorithms sorted in order, a number of which we'll cover during the semester, but not all of them. So it goes from dense Gaussian elimination at the top, which will, of course, solve any system of linear equations, not just Poisson, all the way down to an algorithm called multigrid, which attains the lower bound. So what's the lower bound? If I'm trying to solve an n by n linear system and my output is of size n, I have to do work at least n things, right? So n is kind of a trivial lower bound, and this is all in a big O sense, and multigrid actually gets you there in terms of how much arithmetic it does. And of course, Gaussian elimination costs you n cubed. It's a bad idea for Poisson, but it solves any problem, and people care about making that run in parallel too. So the first thing you might notice about this matrix is that it's banded. There are a lot of zeros out there, and if you take advantage of that, there's an algorithm called band LU, and that gets the complexity down from n cubed to n squared. That's a big improvement. It works on any band matrix. It's interesting to parallelize, but it's not quite fast enough. There's another scheme called Jacobi that just does sparse matrix vector multiply, and we can parallelize that very nicely, but it's also just an n squared algorithm. Now, another thing that you might consider doing is saying, I have to solve this problem so many times. It's the same matrix. Why don't I just invert it once and for all and just keep the inverse around and just multiply by it whenever I need to solve, right? Because it's the same matrix all the time. That doesn't do any better. If you compute the explicit inverse and just say that's free, I'm not going to count that, and just count the time to multiply by it, it's still n squared. So we need to do better than that. There's algorithms that are also kind of sparse matrix vector multiply. There's something called conjugate gradient. That takes advantage of another property of the matrix, something called symmetric, because it is symmetric, and also because it's positive definite, all its eigenvalues are positive. That gets the complexity down from n squared to n cubed into the 3 halves. That's a good idea, and we will have a number of lectures on how to make that run fast. There are variations on this, red, black, SOR. I won't talk about it until later. Then you could do sparse Gaussian elimination. You could try to actually solve it, but take advantage of all the zeros. That's also n to the 3 halves, but that works on a general class of matrices more than Poisson. Yes?
So you showed a picture of, this was a really long time ago, I think it started in relation to this, where...
Look, I'm going to ask you to speak in the mic.
You had a picture that showed that there was a matrix that was very sparse, so there was a bunch of zeros, but you somehow picked the values that you were interested in, 1, 3, 5, and 8 or something.
Right, and only stored those values, right? And that's what this sparse Gaussian elimination would do. You would hand it the matrix in that same format that I showed you before, just a list of all the non-zeros and a list of where they are, and it would do Gaussian elimination, as we understand, the same mathematical algorithm you learned a long time ago, but it would take advantage of all those zeros and not work on them and not store them.
Right. But you still have to pay attention to them, the zeros,
Oh, it's a
right?
very complicated algorithm.
Oh, I see.
I'm not pretending it's easy. There will be a lecture later. I'm just sort of, and many very highly engineered libraries have been built, so you don't have to build them. You should know that this is a well-engineered problem. I mean, there's still research to be done on it. But all of these algorithms that I'm putting here have highly developed software libraries that are available that may just fit your purpose perfectly now. And so your goal should be to say, what structure does my problem have? If I just have a general dense matrix, I got to use that algorithm. And so I'll find the best implementation of it, but that's what it's going to cost me. But if my matrix happens to be banded, then I should look in my library for the best banded version, and I should use that one. And if I have a very sparse matrix, then I might be able to work my way down the list to this sparse LU, and it's a different library, but it's still implemented very well. And finally, if I really am solving Poisson's equation, and that's all, then I could use either the fast Fourier transform, the FFT, or an algorithm called multigrid and get pretty much close to optimal. So all of these have been highly optimized. As I say, there's still open research questions to make them better. But these, and which one you use depends on how much structure your problem has. The more structure, in this case, structure is measured by how close you are to Poisson. That's not the only structure in the world. You'll try to go down this list as close as possible to the bottom. So this column is just counting flops, serial complexity, how much work it is. This column says in a magical model of parallelism where I can have as many processors as I want and communication is free, so it's kind of dream world. This is how fast you could go. And so this is sort of the limit on how parallel you could go. And the answer is you can get pretty close to log n. And log n is a lower bound. How much memory do you can you use? And there's another column for this. Now this is a too simple model. PRAM is a perfect parallel RAM model. We will have real models of communication and say what's the best way to do it to minimize it later. But this is just sort of an outline. So in the black, let me say, why do I have two colors here? People solve Poisson's equation in 2 dimensions. That's the black data. And people also solve it in 3 dimensions. And the complexity changes slightly, and you get the red numbers instead. And it's almost sorted the same way, not quite. Okay. So this is an overview of the algorithms, and I have more details here on the next slide, but I'll skip that right now, sort of explaining what each one is. Okay, so here is just some examples of some very old performance data, but I'm putting it up here for a reason. So this was on a measly little 1,000 processor machine that they had, which was one of the biggest in the world a long time ago. Here are 3 solvers that are taken from that list: Jacobi, Gauss-Seidel, and multigrid. Now I want you to notice that multigrid is hard to implement very efficiently. It's only running per processor at 318 megaflops on this ancient machine. And the other ones you can tune to run a lot faster. But look, the other ones are doing 3 orders of magnitude more arithmetic, and so the CPU time is running, is 3 orders of magnitude smaller. So the fact that these can be implemented, sort of the inner loops are much, much faster, is totally outweighed by the fact that the math is better, that it's doing 3 orders of magnitude less mathematics. And so we will spend some time trying to tune the inner loops of these algorithms to make them go as fast as possible, but getting the math right and choosing the right algorithm can far outweigh all of those considerations. Okay. So here is sort of a summary of what we've talked about so far. So we have both, so just like with ODEs, there's 2 classes of approaches. Explicit methods, which are basically a sparse matrix vector multiplied every step, and there's graph partitioning and all that kind of stuff. And then you have implicit approaches, where at every step you have to solve a sparse system of linear equations. And that lets you take larger time steps and still get the right answer. And so I talked about the fact that there's this correspondence between, so I talked mostly about grids, where my matrix was defined on nearest neighbors in a mesh. And what I'd like to do now is say that not all computations look like that. Not all PDEs are defined on nice regular meshes, and I'd like to give you a little tour on what practical meshes look like and say how the ideas have to generalize. So 1 and 2D and 3D meshes are building blocks. We have to get those right. Those are going to be used to build larger, more practical ones. But practical ones are often very irregular, and we still have to deal with them. So one way they can be irregular is they can be just built out of regular ones glued together. And I'll have a picture of that. So you may have so for this building, each girder may be a nice regular 3D mesh, but they're connected in whatever irregular way you have. So overall, the matrix is not regular. You could have completely unstructured meshes. And so for Darth Vader and all that material stuff, there's certainly, you saw those pictures, there were very irregular meshes underlying whatever pictures the artist chooses to draw. And then you also have adaptive meshes, because as the thing you're simulating changes, the action moves. So a canonical example is you have a flame front burning in a gas. And you need to have a very fine mesh around the flame front because there's a lot of action there. You have to very finely resolve what's going on. But as it burns, the front moves. You have to change the mesh to follow the flame front. So you have to do that adaptively as the thing burns. And that comes up in other places too in graphics. So if you walk on the 5th floor of Soda, you see lots of meshes on their videos about how they change from time step to time step. So how am I doing here? Okay. So let me now talk about parallelism in regular meshes for one slide, and then go on to how I composite them and what that looks like. So if I have now a 2-dimensional mesh, so everybody's connected to their north, south, east, and west neighbors. Again, the most natural thing to do is to divide it up into squares so that every processor owns a square. So I have 25 processors, and each one is going to own a subset of the mesh points. So you should think of this big square representing a very, very fine mesh, and each processor gets n over 5 by an n over 5 submesh. And they're going to do local computations to update their neighbors. So a picture we've seen before. And so what communication is involved? Again, it's nearest neighbors. And so the only communication that's necessary is going to be with the neighboring processors. And so what people do in these algorithms is that they build their data structure so there's some extra space on the borders so that when they go to the neighbor over here and say, tell me who's right on your border, there's space available. Those are called ghost zones. So that's a typical structure that people build. So now let us take that and apply it to something slightly more interesting. So here is a discretization of a cross-section of, let's say, a bridge abutment or something like that. Kind of made it up. So every chunk of material here is completely regular. That's a perfectly regular two-dimensional mesh. And so there's a row or a column of your matrix for every mesh point you see there. And every edge represents a non-zero. So the fact that there's an edge from there to there says if that's row 1 and that's row 2, then there's the 1, 2 entry is non-zero. And I have another separate mesh down there, a mesh there. And so this is what my material looks like that I'm going to try to discretize. So what I have to do now is number them. I have to build a matrix out of it. So what I'm going to do is take the first 49. This is a 7 by 7 mesh. So I'm going to take the first 49 entries, and I'm going to I'll color them green. Those are going to be the first ones. Then I'll take the next mesh, which is of size, I think, 5 by 5, and I'll put that next. Then this one, then this one. And when I do that and put it in a matrix, this is what the matrix looks like. So here, these 49 entries, that corresponds to these 49 green entries up here. Then the next 25 or so entries, this blue mesh that corresponds to here. Then comes the pink part, that's here. The light blue part, that's there, and so forth, working my way around. Now, this matrix is, you're connected to your nearest neighbors, so it's the same kind of band matrix we saw for Laplace's equation. So if I were to zoom in on this picture, you can imagine it will look just like Laplace's in terms of where the non-zeros are. I mean, the entries depend on the physics, but the non-zero locations look just like you're connected to your nearest neighbors. So that's a matrix with, let's say, 5 or some number of diagonals. This blue one is the same. That one's the same. But is it easy to see that there are a lot of red dots here? There are a lot of little off-diagonal dots. And those correspond to the fact that these chunks of material are connected to one another. So these red dots here are edges between the green and the blue, and so they're up here. They're off-diagonal. And that's, you've got to put them there because the thing is connected. Then there's the purple and the blue are connected by some red edges there. So there, I think that's right there. And as I come around, I get some really distant ones. So here's some ones way the heck out here. So who are they connecting? They're connecting this green part, the first part. And they're connecting this blue part down here. So these are these red edges here. And because this thing is kind of a circle, no matter what order I put it in, somebody's got to be pretty far away from the diagonal, right? Because it's just, I can't straighten it out because it's all connected. So let's see what happens now if I actually do Gaussian elimination on this matrix as I've written it down. And I use an algorithm which only does arithmetic and stores the non-zero entries. So here's a picture of the matrix. I've left out the colors now, so all the black dots are the non-zeros. And here's what happens after I do Gaussian elimination, or actually Cholesky on the algorithm. What I've done here is I've drawn in all the non-zeros, put a little dot where I get a non-zero. The black ones were there already, and the red ones are all new. So I had to create new non-zeros where they weren't before because of the ordering of this matrix. So when I added a multiple of one row to another row to create zeros, I mean, it's just Gaussian elimination, I had to add non-zeros to previously zero entries, and so I created all this extra storage and all this extra work. And I have up here how much work I did. It turned out to be a small problem, 300,000 floating point operations to do it. So now the question is, what's the right order to do this in? This order was perfectly natural. It's what the engineer would write down. It's how you would solve the problem. But it's a terrible one from the point of view of either, of complexity of solving it on a computer. Either a sequential computer or a parallel one, I don't want to order the matrix this way. Any ordering the rows and columns gives me a matrix with the same answer, as long as I keep paying attention to the ordering. So let me try a different ordering. And so here is an ordering chosen by one of our combinatorial algorithms that we'll talk about later in the semester. So these two matrices are the same. All I've done is permute the rows and columns. in a certain way to try to minimize the amount of work. And it's something called minimum degree ordering. So these matrices are the same, believe it or not. So now let me run Koleski on this guy. Here are the non-zeros. How many do I, they're all red again. They've dropped from about 12,000 to 6,000. So I've cut that in half. If it were a larger matrix, it could be an arbitrarily large drop. And the amount of arithmetic has dropped from about 300,000 to 200,000. So how did I choose this order? Well, not surprisingly, choosing the best order is NP-complete. So we will use approximations. And it turns into a variation on the graph partitioning problem that we had before, choosing the right order. And if you want to play with this in MATLAB, you can just grab this in MATLAB. You just do NASA airfoil example in whatever the right directory is. You get, and you can plot it, and you get this picture. And if you do a SPI plot of that matrix, this is what it looks like. And if you do Koleski Gaussian elimination on it, this is what it looks like. So you can play with this now if you want on your laptop. So let me give. So this is one example. You take regular meshes and you kind of glue them together. Here's an irregular one, but the same effect comes up, which is that you have to choose the right order, or you get a lot of non-zeros and a lot of work you wouldn't have otherwise. So let me go on and just say where some other meshes come up. So this is an example that comes out of multigrid. This is the system of, here is the mesh that is given by the engineer. It's a nice tapered tube, nice and regular, talking to the neighbors. And it turns out in order to solve this quickly, we're going to produce a sequence of meshes which are kind of every other mesh point, kind of approximated. So I can sort of get coarse approximation. So this mesh is generated automatically from that one by sort of taking every other mesh point and just connecting one-away neighbors to sort of get an approximation. I do it again. I take every other mesh point. I get this thing, which still kind of sort of resembles what I started with. And I do it again a few times, and I finally get this approximation to the original one. And I still have to do sparse matrix vector multiply in all these meshes. They're generated automatically by the algorithm, and it's a challenge to do. So let me do a biomedical example. So this is work that actually won the Gordon Bell Prize for the best parallel simulation of a large, real problem on a supercomputer a number of years ago. Work by Tony Kevney and Panos Papadopoulos in mechanical engineering, and a colleague, former student, Mark Adams. So the goal is to predict the failure modes of people's bones. So the question, so people get osteoporosis, their bones weaken. You'd like to know what is the likelihood that by taking a bad step or falling or tripping that their bone will break. To do that, and the first thing you need to do is, and people do that now by estimating bone density. It turns out not to be a very good predictor. What you'd like is a much more accurate model of whether a person is likely to break their bones. So what these folks did was that they took a real bone from a real person, a cadaver, and they did a complete finite element analysis of it to figure out when is it likely to break. And so what they did is they built a linear system, which I'll show you a picture of on the next slide. And they took that linear system with the finite element model, and they started pressing on it and said, when will it break? How much pressure has to be put on this bone for it to break? And then they did the same experiment in the laboratory, and they matched. So here's how that was done numerically. So they took the bone, and they did some mechanical testing to find the failure mode. And they also needed to build a perfectly accurate three-dimensional model of it. How did they do that? They did a micro CT scanner. By using much higher radiation than you'd use in a living patient, you can actually get a fully resolved model of what every little tiny piece of bone is, down to 22 microns. Okay? And so here's a 3D image that was extracted. And bone is mostly air, right? So you have to resolve it at that level of detail in order to figure out where the materials actually are. And they ended up with a finite element mesh with 537 million degrees of freedom. So this is why they needed a supercomputer to do it. And so they took a piece of this. I don't think they had the entire vertebrae, but this is a totally accurate model of one piece of the material. And they did a finite element model, and it matched. So, and for that, they won the Gordon Bell Prize. So what does this mean for actual practical medical use? Because you can't take the bone out of the living patient and do this analysis. So what Tony is doing now in a startup is you can take a much lower resolution image of the patient, do a lower resolution finite element analysis, and still come up with clinically useful information as to when the bone is likely to break and advise the patient appropriately. But it all began with this very high performance computing kind of analysis to sort of justify that it was possible to get the truth out of these simulations. So that's one. This is a very irregular mesh, and it just comes out of the CT scan. So the other kind of meshes that come up in practice, as I said, are adaptive. And here's an example from I believe, a supernova simulation that was done at LBL. So here's the inside of the supernova. There's a shock wave propagating outside, and there's a lot of interesting action at the surface of the shock. And so there's a mesh here, which is superimposed. And as this shock changes, you have to change the mesh so that you just resolve the forces right along the side. And of course, it moves outward very rapidly as the supernova explosion continues. And the author of this code is one of your teaching assistants, Brian Van Stralen. And so sometime later in the semester, there will be some more information about how this particular kind of code works. Here's another example, and I believe this is taken so this is gas dynamics where you have a shock front between two different gases, and again, the mesh becomes much, much finer in the middle where they meet, and it moves over time depending on where the shock wave moves. So there are lots of challenges here. It's certainly fun to draw pretty pictures, but you have to generate these meshes in the first place. So sometimes you have hard data, in the form of a CT scan. Other times it's generated by the simulation. Once you discover where the complicated chemistry is happening, in a shock front or in a burn front, then that's where you put the mesh. And to do the geometry and actually put down the meshes is quite a challenge, and there's a lot of software that's been developed that you don't have to rewrite. Our colleague, Jonathan Shuchuk, has written one of the leading two-dimensional meshers called Triangle. There's a lot of other software that's more complicated that works in 3D. But certainly these codes exist. Then there's the question of how do you assign them to different processors in order to minimize communication, give everybody an equal amount of work to do. I talked about graph partitioning. There is a lot of graph partitioning software. Parmetis is just one example of many. We'll have a lecture later in the semester. We'll talk about the algorithms, but there is a lot of well-developed software that does this for you to do the iterations. Then there's a question of how do you do the solvers themselves. And I mentioned it all comes down to sparse matrix vector multiply, and if you're doing an explicit method, or it might come down to sparse Gaussian elimination or multigrid. If you're doing an implicit method, there's a lot of code, again, that's been developed that way. A lot of libraries. We will talk about the algorithms, and there's a lot of open research questions about how to make them better. But in the meantime, there's a lot of software that runs in parallel in a lot of different machines, and we will point all that out as we move forward. So to summarize, this is the summary of now finally all 4 different patterns. So we did discrete event systems, we did particle methods, we did ODEs, and we did PDEs. And we saw all of these 7 dwarfs come up before, as we had before. And so just let me go to this picture so I don't have to list them. We saw structured grids. That was Laplace's equation. We saw dense matrices come up. We saw sparse matrices. We saw FFTs. We saw n-body, gravitational force and n particles. We saw there was some embarrassing parallelism. And we saw work on lots of unstructured grids, like the human vertebrae. And so all of these 7 red boxes indicate they come up in high-performance computing everywhere. And so we will have certainly lectures moving forward in the semester on them. So I think that is where I want to stop. So what are we going to do next? So we've sort of toured the whole stack at this point. We've looked at the application level and said, is there natural parallelism, natural locality? We've looked at the hardware level. And so now it's time to go back to the middle of the stack. And we're going to talk about the programming models for the next few lectures. How do you actually write the parallel programs that express all of these things? So we'll start with shared memory parallel programming for a lecture, and then we'll move on to distributed memory parallel programming as well.